Welcome to 6th week of computational quantum chemistry. And this week we are going to discuss about density functional theory or DFT, which I believe will be interest to most of you. And many of the times the word DFT is actually used synonymous to the word computational chemistry, which is not true because there are much more than DFT in computational chemistry, but often I get the statement that they want to learn DFT. What they actually mean is that they want to learn computational chemistry, and also many of the time I get to hear that okay, you do DFT, that means they want to ask, do I do computation chemistry? And DFT is also has become synonymous with a particular functional that is called B3-LIP. So this week we are going to know what is density functional theory, what this words B3-LIP actually means, and what is more into DFT than B3-LIP and how you can use it. So let's start one by one. Just to give you a small hint that in this week we are going to have a slightly more theory than practical than we generally have in our classes. The reason for that, there are very little literature is available in DFT in terms of learning where you can get a proper view of the courses. So just before I start the lecture, to give you a hint that in this week we are going to discuss a little bit more theory than what we usually do. Because although a lot of literature is available on DFT, there are very few places where it is given in a very concise format so that you can actually get to know the basics and try to make sense of the calculation. The other thing is that density functional theory actually involves a lot of mathematics, which chemists are not very comfortable often. So the theories of DFT generally chemists tend to avoid, and of course chemists use the DFT a lot, but they somehow want to avoid the theory. So here I will try to give a little bit background so that you can follow whatever is come from your computational chemistry output file. Now to start with the basics, what is the problem in the standard wave function based methods? We have seen that electron correlation method can lead to high accurate energies. If you are ready to do couple cluster in a big basis set, you can get almost within 1 kilocalorie per mole of the experimental result, the so called chemical accuracy. However, this accuracy comes at a significant computational cost. If you are doing CCSD, it is 10 to the power 6. If you are doing parenthesis T, it goes to 10 to the power 7. Of course, you can use lower scaling technique like density fitting, chain of sphere approximation, local correlation technique. But still this reduces the prefactor, sometimes cuts the scaling a little bit, but still the cost of computational scaling, storage requirement, memory requirement limits this application of these methods to relatively small molecule. And why? What is the problem? Because just think of this equation, H psi is equal to E psi, and let us think of solving H psi is equal to E psi for a simple molecule water. 3 atoms, it has total 10 electrons, 8 from the oxygen and 2 from the 2 hydrogens. So for this 8 electrons, each of the electron has 3 spatial coordinates. So the Schrodinger equation will become 30 from the spatial coordinates and 10 spin coordinates to a total of 40 dimensional problem. This is just for water. And for n electron system, it is 3n plus n number of dimension. Of course, you can tell that in some cases I can just integrate out the spin and forget out the spin, but if I want to have a general picture, it is 3n plus n number dimensional problem. So this dimensionality actually start to hit you hard when you go for large and larger kind of systems. And remember, this it's not that something which was not realized. One of the very important statement made in the beginning of quantum mechanics, which Dirac did, and we have discussed about this statement, that these fundamental laws necessary for the mathematical treatment of large part of physics and the whole of chemistry are completely known. It's right. If I have the equation H psi is equal to E psi, and the difficulty lies only in the fact that application of these laws leads to equations that are too complex to be solved. Because if I use this equation on water, I will get a 3n plus n dimension problem, a 40 dimensional problem, even if I forgot any other details. So these equations will be too complicated to be solved. So that means the wave function theories, you cannot go for very large molecule accurately because of the fundamental nature how the equation looks like. So we have to think of a better way. What better way we can have? Think what we can do. One of the things can be electron density, because remember Wave function does not have any physical interpretation. What we actually work on is in terms of probability density. Psi star psi we know is equal to probability density. So, I can write the electron density as this quantity, this psi star psi, where r1, r2 up to rn are the coordinates of electron 1, 2, 3, 4, 5. Let me change it to my proper laser pointer. Yep. And so, electron density gives you an idea how at a particular point my electrons are localized. So, I can get an idea of that. The advantage of that, electron density will only is a 3-dimensional quantity, and life will be very good if I can write the energy as a functional of the density. Why I use the word functional not function, we will come to that, and remember there are 3 things: density, functional, theory. So, we will go one by one, what is density, what is functional, we will, and what is theory in this density functional theory, maybe not in the same order as the name suggests. So, life will be good if energy can be written as a functional of the density. Then the advantage is that 3 dimension reduces to 3. So, and the advantage is that there is no independence. So, it does not matter how big my molecular system is, or how I am working with a big protein or a cluster, I can still, my problem is a 3-dimensional problem. So, it will not scale with respect to the size of the molecule. So, I can, in principle, I can use, if I can write the energy as a function of the density only, I can use it for any dimensional system, any large molecule, I can do computations on the top of it. And we will come to see is it possible or not, but before going that, let us go to the words one by one. Let us first see what the functions are actually as. Remember, there is an existence theorem which says, and we will come into that, that is Wenberg-Kohn theorem, which says that there is a functional which exists. But problem is that no one knows how the functional looks like. We know certain things about the functional. So, the situation will be similar like blind people trying to describe elephant. Some of them will find it like a pillar, some of them will find it like a wall, some of them might be finding like a snake. If someone is touching its teeth, then it will find it like a sword, but that is not how an actual elephant is. I have created this picture with ChatGPT. It is an interesting software, you may use it in your practical problems, but remember, ChatGPT does not always give you right answer. It is actually quite good in giving wrong answers very confidently. Secondly, in many of the cases, when you use this ChatGPT for solving exam problems or solving or writing manuscripts, it is not strictly legal. There are maybe plagiarism issues. So, make sure if you use it for something important, make sure that you have the required permission for doing that. So, that means what I have the information about this functional which maps the density to the energy, I do not know the exact form of the function. So, I am like, we are like these blind people who does not know how the elephants actually look like. We know that there is an elephant, we have heard that there is an elephant, and there is a formal proof that there is an elephant, but we do not know what it looks like. In the similar way, we do not know how the functional form of that exact functional. We only know certain properties of the functional, and from there we will try to guess how this functional can be. And the whole density functional theory works on that same fact that everyone tried to give a guess. Now, it is your guess versus my guess, and there is no clean answer which is the best way, and there is also not a clean answer how I can improve my guess. So, someone can start with one guess and there is no unique way to know that which guess is better than the other and how I can improve upon it. That is a problem then in the wave function based theory, because in wave function theory, especially if you are using systematic methods like couple cluster, you can always get more accurate answer if you are ready to give a little bit more computation cost. So, that is a particular problem in the density functional theory, is that you do not have a systematic way to improve it, whereas in wave function based theories it was good. If you are using a systematic wave function method like couple cluster, you can always get more accurate answer if you are ready to pay a little bit more computation cost. Whereas in the density functional theory, there is no unique way to improve your accuracy of your calculations. Okay, let us now go to the word what is a functional. Before going to the function, let us take the word function. A function takes a number as an input and produces a number as an output. So, for example, I have this function fx is equal to x square, where this function maps a number x to its square. So, this is what a function looks like. Now, what is a functional? So, in the case of function, it takes number as an input. In the case of a functional, it takes a function as an input and produces a number as an output. For example, let us look at this functional. So, this functional f is a functional of rho, and rho depends upon, rho is a function because rho depends upon the position, and this form of the function is rho square dr. So, this f maps the input function rho r, that is electron density, to a scalar value calculated through the integration. Remember, a functional will take function as an input and the output will always be a number. So, this is what the word functional means in the density functional theory. Now, we were discussing that life will be very good if I can write the energy as a function of density. So, I will give density as an input and it will give me the energy as an output. So, the definition of functional works here. So, I will give the density, which is actually a function of position, and my energy, a scalar value energy, will be my output. Now, why do I think that will work? Let us see. So, this is what is given here is a density profile of CO molecule. I have plotted the density with respect to the position, and you can see there are two cusps. One is a position, and the cusp generally happens at the position of nuclei. So, there are two nuclei, oxygen and carbon, you see two cusps, and you can see there is a height difference between the two cusps. That means, if I get this density plot, the integration of density will give me the number of electrons. That is clear. So, if I take the rho of r and dr over the entire volume, total number of electrons will be n, number of electrons. Secondly, the cusp in the density define the position of the nucleus. So, I can find out where the nucleus is. Moreover, you can see that there is a difference in the height of this cusp. So, from the height of this cusp, I can find out what is the corresponding nuclear charge. So, I can use this relation del rho of del Ra, and that will be is equal to minus 2 Z A of rho r. This rho with dash is the spherically average density, Z is the atomic number of A, and Ra is the radial distance from A. That means, if I get the density profile, I can find out the number of electrons, I can find out what is the position of the nucleus, and I will find out what is the nuclear charges. That means, whatever is required to define my Hamiltonian, that information is already contained in the density. So, that means, as I can get the energy by solving the Schrodinger equation from the density, I should be able to get the energy out of it, because all the informations are actually contained in the density. Okay, so that is good. Now, let us go to mathematically know what is density. Before going into know, what we need to know what is called a density matrices. What is a density matrices? The n-body reduced density matrices is derived from the full density operator of a quantum mechanical system by tracing out the degrees of freedom of m particles. That means, if I have total n number of particles, I will trace out few of them. So, like m number of densities I will trace out, and rest of them will give me an n-body reduced density matrix. Maybe look like a very difficult statement. Let us say I have a wave function psi, and this wave function psi has a coordinate from r1 to rn plus 1 up to rn total. Now, among this from rn plus 1 to rn total, that is the number m, this I will trace out, that means this I will integrate over, and rest r1 to rn, this will remain, and that will give me n-body reduced density matrix. Reduced density matrices are generally represented by gamma, and so density matrices are represented by gamma, and density is represented by generally the word rho. This is the convention, and this is what we are going to use. So, because I am now integrating over this m coordinates, what I will be left with is an information about n-body, and that is why it is called an n-body reduced density matrix. It is a reduced because already my m dimension has been integrated over. And in this case, psi is the full wave function, which has a total coordinate of 1 to n total, which is n plus m. Ri is the spatial coordinate, and maybe it can be spin coordinate also. For the time being, let us only work with the spatial coordinate, and gamma n is the reduced density matrix of subset of n particle. So, this is a generalized n-body reduced density matrix. Now, let us come to the special case. The special case is one body reduced density matrix gamma 1. So, in place of leaving n number of variable unintegrated, if I just have only one variable left and rest integrate all the other variable, that is called one body reduced density matrix, and this one body reduced density matrix actually plays a very important role in the density functional theory as well as in natural orbital based theories. Remember how we were generating this natural orbital? We were generating the natural orbital by diagonalizing a correlated one particle reduced density matrices, and that will give me a better set of orbital. If I take an uncorrelated one body reduced density matrix, so a reduced density matrix obtained from a mean field calculation, that will give me the Hadron-Fock orbital. So, the expression for the one body reduced density matrix, that is gamma 1, this looks like this. So, this is n electron is the normalization factor, and from the coordinate from R1 to Rn total, I will integrate out everything from R2 to Rn total, only leaving the coordinate of electron 1. See, in the reduced density matrix there are two coordinates left because R1 may not be same as R1 dash. So, one body reduced density matrix will have two variables R1 and R1 dash, they may not be similar. Now, that is one body reduced density matrix. Similarly, I can have a two body reduced density matrix which gives the joint probability of finding two particles. So, that means I will leave the R1 and R2 left like untreated, and R3 to Rn total I will just integrate them over, and that will give me a two body reduced density matrix. So, which will have four coordinate R1, R2, R1 dash and R2 dash. Now, the diagonal component of the first order reduced density matrix, if I take the one body reduced density matrix or first order reduced density matrix, remember it has two coordinate R1 dash and R1. If I set R1 is equal to R1 dash, that gives me electron density function rho 1. Often it generates used without the subscript 1 when higher order density matrices are not involved. So, density is nothing but the diagonal element of the one body reduced density matrix. So, here R1 dash is equal to R1, and from R2 to Rn total I have integrated them out. So, the integral is a probability of finding an electron, it does not matter which electron since they are indistinguishable at position R1, and the prefactor in electron ensures that the density integrates to the number of electrons. Now, I have came to know what is density, what is functional. Now, we need to find out the theory. Before going that, let us see what we can do from the reduced density matrix. Remember, there is a difference between one body reduced density matrix and density. Density is just the diagonal element. So, one body reduced density matrix actually contains more information than the density. Density actually contains much less information because it only has a one coordinate R1. So, in principle, if I think of x, y and z, it only has three coordinates. Does not matter. I am calculating with the density of 1 water, 10 water, 1000 water, 1 lakh water, 10 million water. In every cases it only have three variables. That is the advantage of using the word density for doing calculation. Now, the way I have generated density from one body reduced density matrix, if I set R1 dash is equal to R1 and R2 dash is equal to R2 in the two body reduced density matrix, I will get the electron pair density or rho 2. So, here you can see my R1 is equal to R1 dash, R2 is equal to R2 dash. From R3 to Rn total I have integrated out all the possible coordinates. So, this integral is the probability of finding an electron at the position R and another electron at the position R2, and the n electron minus 1, this prefactor ensures that the density that rho 2 actually integrates into the number of unique electron pairs. Now, I have came to know electron density, electron pair density. Now, what I am left with is how this can be used to actually define energy. Remember, my final aim or final dream is to write the energy as a functional of density, only density, not density matrices. So, if I think of an energy of a many body wave function, I can write the energy as an expectation value if my size and well behaved wave function. And remember, I don't at this moment, I don't claim that psi is a single determinant. Psi can be a multiple determinant also. So, psi can be a CI wave function, MP2 wave function, couple cluster wave function, Hartree-Fock wave function also, but at this moment I don't make any claim that it has to be a single determinant. Of course, in the case of single determinant, what we will get is a lot of simplification. So, I know the Hamiltonian actually has 4 terms. First is the kinetic energy, second is the electron nuclear attraction, electron electron repulsion and nuclear nuclear repulsion. The nuclear nuclear repulsion is actually a classical term. I am of course writing the many body wave function in the Born-Oppenheimer approximation. So, nuclear nuclear repulsion is an additive scalar term. So, it does not really matter how I add it, it is just a number, but rest of this 3 term, the first one read is the electron electron kinetic energy, and in the subsequent discussion we will represent it always with T, kinetic energy. The electron nuclear attraction, I will write it as VNE, electron electron repulsion is VEE, and of course nuclear nuclear repulsion is VNN. So, this is the nomenclature we are going to use. So, before we start the formal discussion, let us make the nomenclature very clear. Now, how can I write this energy? This T, Ne and V has as the definition as the previous one in terms of reduced density matrices. So, writing them in terms of reduced density matrices, this will be the expression. I will not going to derive it. If you are interested in the derivation, you should follow the density functional theory by Parr and Young. Maybe I will give a link in the slides. If you are too much interested, you can go and try to derive them itself. It is a good exercise, but I will not go into the derivation in this class. But what is important? Just see the form of the expression. The potential energy in this case, the Ne and the E can be written in terms of rho 1 and rho 2. So, the nuclear electron potential energy can be written only in terms of the density, not density matrix. I do not need the rho 1, whereas the kinetic energy is, this is the only part where I need a density matrix. So, see, kinetic energy cannot be written in terms of density alone, it need to be written as density matrix. Stop the lecture video here and think it a little bit. So, to define the energy, I actually have 3 terms: nuclear electron attraction, electron electron repulsion, kinetic energy. Nuclear nuclear repulsion is a scalar term, so does not matter. Now, nuclear electron attraction can be only written in terms of only density. So, that is good. That means I do not have orbitals, I do not have wave function, I do not have 3n dimensional problem. I only have a quantity which is written only in 3 dimension, does not matter how big system I get. Now, the 2 electron part, the electron electron repulsion, it of course, if I go into an Hartree-Fock picture, I can write them as a Coulomb and an exchange. The Coulomb part will only depend upon rho 1, that is the density, and the exchange part will depend upon rho 2. Of course, rho 2 has 2 coordinate, r1 and r2, 6. Still not bad. What will give me the major problem is the kinetic energy term, because the kinetic energy term cannot be written in terms of density alone. I need the one body reduced density matrix, and that is a problematic thing. How I am going to get into that, and this will make the density functional theory more difficult in terms of practical computation, because you cannot write them only in terms of density. So, you need to take approximation, and because of this fact you need to give away the orbital, you need to bring back the orbital picture back in the density functional theory. The whole aim of density functional theory was to remove the orbital picture, because I did not wanted to do the orbitals, because this gives me too many dimensions, 3n dimension. I wanted to do it in a 3 dimensional way, but because the kinetic energy term depends upon the density, it's actually I need to bring back the orbital picture to get this one particle reduced density matrix. Now, this relation as it is written, it is an exact relation. I can write the energy exactly in terms of one particle reduced density matrix and the 2 particle reduced density matrix, or you can integrate out to rho 2 also. And this form of the energy can be written for any form of the wave function even for a complicated many body theory like couple cluster, if I get the one body and two body reduced density matrix, I can always write the energy in terms of that. Question is that how I can get the one body or two body reduced density matrix. Of course, I can solve the wave function method and then integrate out the rest of the coordinate to get into one body and two body reduced density matrix. But then I am again went back into the problem of dimension, because if I solve the wave function method, I still have the problem of solving for 3n dimension. So, writing the energy only in terms of density matrices does not give me any advantage over solving a wave function method, unless I have a direct way of solving for one body and two body reduced density matrices. So, next we will come to that, where we will try to solve the energy equation in terms of one body and two body reduced density matrices.